Namaskar. We are here today to talk about the basics of light microscopy. As we are all the students of microbiology, it becomes imperative that whatever studies that we carry out regarding the microorganisms of different varieties, the use of microscope of different varieties is necessitated. Uh, as the students of microbiology are already aware, the fundamental types of microscopy are the light microscopy and the electron microscopy. We are today going to talk about the very basics of light microscopy. How do different types of light microscopes work? What are the principles involved in the manufacture and working thereof? And what are the basic techniques by means of which we get an image where we can make a proper study of the microorganisms under study. As the first slide will show us, we begin with the properties of light. As we are all aware, the light is one variety of electromagnetic radiations, and the wavelength falls in the range of 400 to 700 nanometer. It can also be equilibrated to 4000 to 7000 angstrom units. And the waves of light, the natural light consist of different waves, and the basic variation among those waves falls in the wavelengths of different varieties. Let us have a look at how exactly the light rays are propagating. As I told you in the beginning, light is propagating in the form of electromagnetic radiation. You can see here very clearly the components, two different components of the light waves, the electric component and the magnetic component, are propagating perpendicular with reference to each other, and that is how the light is propagating. The next slide will show you how exactly the light progresses in the form of a wave, and you can see the different waves of light with different wavelengths are of different color. Let us see that again, that will make the point very clear. The first at the top shows the spectrum of the light, different wavelengths, and then this is how the light propagates, the electric component and the magnetic component. And once that happens, you can see this wave progressing and progressing and progressing, and depending upon the wavelength, different colors of light are being formed. The next slide shows us a very important property of the light with reference to the development of the microscopes. When the light rays are progressing, transmitting across a prism, they fall into different colors. The reason behind this is very simple. The different wavelengths of light are bent, are refracted at a different angle, and the property of this is made maximum use of in the development of different types of microscopes. You can see different wavelengths are propagating across the prism, and their refraction angle is reasonably different. We can see the same slide again. Look, and now individual ray. Your screen now will flash one ray after another. The first one of the light component, once it hits the prism, you can see it is bending to the minimum, the red light, and then the next, and then the next, and ultimately the violet one, the one with the shortest wavelength and the highest frequency. This is an important property of the light rays. The microscope, as I told you in the beginning, with which routine laboratory work is carried out, is the compound light microscope, and this light microscope is illuminated with natural light or artificial light. As you can see the photographs, this one where the pointer is being placed now is the one which has been fitted with an artificial lamp, and this one is an ordinary microscope with which most students are familiar, is being illuminated by the natural light. More about this will be told by Sneha. Sneha, please take over.
Hello. As you can see on the screen, as have already been shown, two types of the compound light microscope. Both are used very commonly. One is using daylight as the source of illumination. The second one is illuminated with the artificial light which is inbuilt in the microscope, and both are used very commonly. Now the next slide will show us the basic functions, that is the compound light microscope, what is the construction and how do we get the magnification. As all of you know that the compound light microscope, which is used in the routine laboratory work, consists of the two lens systems. There are two lenses. One is fitted in the objective and is referred to as the objective lens. The other one is the ocular lens, which is fitted in the eyepiece of the microscope. Now the compound light microscope, it is very economic, easy to handle, efficient, and thus used popularly for routine laboratory examinations. Now let us see what are the basic functions of the microscope served. As you can see in the slide, the first function of the microscope is the magnification. We are dealing with the study of the microorganisms, and all of us know that the microorganisms are invisible creatures, and so to visualize them we need the help of the microscope, and so the magnification is the first important function of the microscope. You can see in the animation which is accompanying that the object which is there in the form of a small dot is not visible, but when the simple magnifying glass, as all of you must have seen and used it somewhere, that you know using magnifying glass it is very convenient to see the objects with small size, because the magnifying glass would enlarge the object, and the same is carried out by the microscope, where the small objects are made visible very easily and clearly with the help of the magnification power of the microscope. Now along with the magnification, the second and probably the more important function of the microscope is the resolving ability of the microscope. Resolution means it is the ability of the microscope to distinguish two small, very closely spaced objects in the form of the dots or the lights. They should be seen very clearly as the separate objects in the structure of an object, and this will be very clear in the next slide, where it has been shown that the objects which are lying very close to each other are initially seen as the single object, but with good resolution, with the good resolving ability of the microscope, they can be seen as the two separate objects, and this is the resolution which is very important, and it serves the function of the resolution, and by the help of the resolution it is possible to study the structural details of the object. You can see in the slide the object which is seen as the single object initially, you can see. Now, with the magnification accompanied by the resolution, now we can see the single object as the two separate distinct objects which are lying very close to each other. So this is probably the more important function of the microscope, and the magnification without resolution would be technically considered as the empty magnification, and it will not make any sense. So both the magnification as well as the resolving power of the microscope are very important in the study of the microorganisms, as they provide enlargement accompanied with the resolution, where it is possible to have the structural details about the object. The next slide shows about the magnification, how actually it is achieved in the microscope. As it has been told that it is the compound microscope, compound light microscope, it makes use of the two objective lens systems, and the magnification achieved is the multiplication of the two lens systems. Here you can see in this slide that is the primary magnification. The first magnification is produced by the objective lens which remains close to the object, and the second and the final magnification is produced by the ocular lens system. Now this will be very clear in the next slide, where you can see the actual path of the light rays. Here you can see the light coming from the condenser lens, it passes through the object. So after passing through the object, it passes through the objective lens where the primary magnification is achieved, you can see. And then this is the primary magnification achieved of the object when the light rays enter the objective lens, and finally they pass through the ocular lens. You can see the pointer is there on the ocular lens, and then the final magnification is achieved, which we can see in the form of the virtual image. Now you know that the microscope which is used in the laboratory is having three different objective lenses with the different objective magnification power. The low power with 10x, the high power with 40x, and the most commonly used lens for observing the microorganisms is the oil immersion lens, where the total magnification achieved is the multiplication of the magnification obtained by the oil immersion objective multiplied by the magnification of the ocular lens. So total magnification that we get is the 100x, and you can see the virtual image which is 100 times magnified, and this is very convenient. This is very helpful in observing the creatures which are of very small size, the microorganisms, and their observation becomes very easy, convenient, and it is accompanied by even the resolution, that is along with the magnification we can also study the different structural details of the organisms. So in this slide we have shown you have been shown the complete light path and how actually the object is magnified, and we can see the final, that is the virtual image of the magnified object. Now the next slide will give you the details of the resolution, how it is actually obtained using the compound light microscope, and that will be discussed by Piyush. So please take it over.
As we have already seen about 4 slides back, the resolution is the ability of the microscope to actually reveal the finest details of the object under observation. Putting it very simply, in scientific words, it is the ability of the microscope to distinguish between two very closely spaced dots or lines. An object which is of extraordinarily small size, which can never be seen by the naked eye, is understood to be magnified by the microscope, but equally important is the fact that it is being resolved. The finer details of the structure of the object are being very clearly revealed by the microscope, and this is a property of resolution. As Sneha has already said, it is probably and arguably a more important property of the microscope. So resolution, as put in the definition, is the ability of microscope to distinguish between two closely spaced dots or lines. But this property of resolution is actually dependent upon a couple of different factors. It is dependent upon, number one, the wavelength of the light which is being employed for the illumination of the microscope, or any other kind of electromagnetic radiation which will be used for the production of the magnified image of the object. And it is also dependent upon the numerical aperture. As it can be seen on your screen, there is a well and properly derived formula for the understanding of the resolving power of the microscope, where resolving power is depicted as D, and this is equal to lambda, the wavelength of the light, which is divided by twice the value of numerical aperture. The numerical aperture actually of a microscope is a very important property of the microscope, and it once again is depending upon two different factors. The refractive index of the medium, which is lying between the object and the objective. Object is always, in case of the light microscopy, the object is always mounted on the slide which is made from glass, and when the light rays are developing on the object, they have to pass across the condenser, and then they fall upon the glass of the slide, then they pass across the object, and finally they move towards the objective. It is this medium between the object and the objective which, in most cases when we are making use of the low power or the high power objective, it is consisting of air. But as we shall be talking later on, some other type of media can also be placed between the object and the objective. So the refractive index of this particular medium plays a very important role in deciding the numerical aperture value, and thus deciding the resolving power value So, the numerical aperture is formulated as n sin theta, where n is the refractive index of the medium which is lying between the object and the objective, and theta is actually the half of the angle which is formed by the extreme rays emerging from the object and entering the objective, as the next animation will tell us. You can see here, this is the objective, and this is the object. O is the object. Now it is being illuminated from bottom, and when the light rays are emerging across the object, you can see these one OA, ray OA and ray OB are the rays which are considered to be the extreme rays. We call them the extreme rays because beyond OA no ray will be able to penetrate the objective, and beyond OA also no ray will be able to enter the objective. So, they are considered to be the extreme rays. You can see angle AOB. This is the angle which actually is depicting the cone of light which will enter the objective at a given time. So, that makes angle AOB as angle twice theta. The value of angle AOB is considered twice theta, and when we divide this angle into 2 by drawing a line OC, angle AOB is divided into 2 angles of the same value, angle AOC and angle BOC, and this is considered to be the theta value. Now, the formula of numerical aperture, as we have already seen, tells us that numerical aperture is equal to n sin theta. N is the value of the refractive index, and then we come to the sin theta value, where sin theta, as you can see here, is the opposite side divided by the hypotenuse, that is AC divided by AO or BC divided by BO. This gives us the idea regarding the numerical aperture. Now, this animation will tell us in better details what exactly importance the numerical aperture and the lambda, the wavelength of the light under use, are holding. Let us see. You can see here, this is the low power objective in operation. What you see here is the cone of light which is entering the microscope objective, and the refractive index in this case is that of air, which is almost 1, because the exact value is 1.00029 refractive index of the air, whereas the cover slip which has been placed above the object has the refractive index of 1.5. Now, see what happens. These are the rays of light which emerge from the object and are entering the objective, and this is the point where resolution is not proper because of the underdeveloped resolving power. Now, you can see we have moved to the high power, and now to the oil immersion lens. You see here the difference in the resolution. As we will put a drop of oil here, concentrate upon this area. Now, a drop of oil will make the world of difference to the final image.